The James Webb Space Telescope will gaze into the past to observe the earliest moments after the Big Bang. It'll collect data on the formation of the very first stars and the very first galaxies in our universe. But there is one mission objective that is far more interesting to me than any other, and that's the mission to characterize planetary atmospheres for signs of life. In this video, I'll be discussing the biosignature detecting abilities of the JWST, what it can detect, what it can't, and how these observations will help us to find alien life. Let's get started. The James Webb Telescope is a 22 meter by 12 meter technological giant about half the size of a 747 aircraft. It's much more than simply a successor to the Hubble Space Telescope. It has 6.25 times more light collecting area on its mirror than the Hubble telescope, and observes a different portion of the electromagnetic spectrum. The Hubble telescope excels at observing the visible light portion of the electromagnetic spectrum, covering the 0.1 to 0.8 micrometer wavelength range, while the James Webb telescope is designed to precisely observe the infrared portion of the spectrum, covering the 0.6 to 28 micrometer wavelength range. The James Webb telescope is designed to characterize the atmospheres of planets by observing them as they pass in front of their host star. As they transit their host star, different molecules and gases in the atmosphere will absorb different wavelengths of light, allowing us to identify the relative quantity of the gases in that atmosphere. To amplify the signal from these absorption events and produce more precise information, we would typically observe the planet over multiple transits and computationally combine the signal. This method of characterizing planetary atmospheres is called transit spectroscopy. While we have been able to characterize the atmospheres of a few gas giant planets outside our solar system, as of 2021, we have not been able to characterize the atmospheres of Earth-sized planets. The James Webb Telescope finally allows us to characterize the atmospheres of Earth-sized planets outside of our solar system. In this goldmine of atmospheric data, there is the potential for detecting the biosignatures of alien life. Biosignatures are pieces of evidence to support the hypothesis that there is or was biological life on a planet. This could include the presence or absence of specific gases in a planet's atmosphere. Now, it's important to clarify the difference between biosignatures and technosignatures. Technosignatures provide evidence of alien technology. This could include radio messages or alien spacecraft. The James Webb Telescope is specifically designed to detect biosignatures. It cannot detect technosignatures. But there are other telescopes designed to search for technosignatures, like the Allen Telescope Array in California used by the SETI Institute. But how do we search for biosignatures of alien life if we don't even know what alien life looks like? At minimum, most scientists would agree that biological alien life would need an energy source to drive metabolic reactions, a liquid solvent to mediate these reactions, and nutrients to build enzymes for catalyzing these reactions. Alien life that fits these criteria may not look like biological Earth life, and may thrive in conditions different than those found on Earth. However, since we know that life is sustained on Earth, a great place to start our search for alien life is to look for Earth-like conditions on other planets. 3 billion years ago, before the evolution of photosynthetic, oxygen-producing organisms on Earth, microorganisms called methanogenic archaea broke down carbon dioxide and carbon monoxide, releasing huge amounts of methane into the atmosphere. This Archean Earth atmosphere contained large amounts of methane and carbon dioxide, but very little carbon monoxide. In a carbon dioxide-rich atmosphere, methane can quickly decompose into other molecules, like carbon dioxide and carbon monoxide. An atmosphere with large amounts of methane and carbon dioxide is unstable. After many years of eliminating potential non-biological sources, scientists believe that this kind of atmosphere can only be created and maintained by biological sources, like methane-producing organisms. The holy grail of biosignature observations would be the detection of a planet with large amounts of methane and carbon dioxide, but very little carbon monoxide. Fortunately, the JWST excels at detecting methane, carbon dioxide, and carbon monoxide, which strongly absorb infrared wavelengths of light. JWST can also detect sulfur gases, methyl chloride gas, and ammonia, which are common byproducts of Earth life metabolism. However, the faint signals from these gases can only be detected under optimal conditions with minimal haze, and by observing a planet over many transits. In addition, atmospheres with these molecules can be maintained by non-biological processes like volcanic eruptions, so their presence may not be evidence of alien life. Unfortunately, JWST will not be able to detect oxygen, ozone, or water on planets outside our solar system, which is a shame because they are major products of photosynthetic, oxygen-producing Earth life, and strong indicators of alien life. So which planets will JWST be looking at? Our best chance of finding strong biosignatures for alien life on Earth-like planets is the TRAPPIST-1 planetary system. This system contains a record-breaking 7 rocky Earth-sized planets, with 3 in the habitable zone. A planet in the habitable zone receives just enough heat from its host star to allow for liquid water. In addition to observing planets outside of our solar system, JWST will observe the moons in our own solar system. Saturn's moons Titan and Enceladus, and Jupiter's moon Europa are all high-priority science targets. We have already identified carbon dioxide on Europa and Enceladus, hydrocarbon molecules on Titan, and methane on Europa, Enceladus, and Titan. We hope to find water on Enceladus and Europa, and nitrogen-containing hydrocarbon molecules on Titan. I'm not gonna lie, when I was first learning about the biosignature detecting capabilities of the JWST, I was pretty disappointed. I mean, we won't even be able to detect water or oxygen on planets outside of our solar system, and those are arguably 2 of the most important biosignatures. But we have to remember that we haven't even started looking for biosignatures of alien life outside of our solar system. In a best-case scenario, JWST will discover Earth-sized rocky planets outside of our solar system with atmospheres capable of hosting life. This would be amazing. And at the worst-case scenario, JWST will begin characterizing the atmospheres of rocky Earth-like planets for the very first time. What was once science fiction will become cold, hard scientific fact. JWST proves that big, expensive scientific endeavors pay off in big ways. It motivates humanity to fund more ambitious scientific projects in pursuit of answering one of the most important questions: are we alone in the universe? I'm Chad Hicks. Thanks for watching.